Everyone can hear me. It is 2 p.m. Pacific, 3 p.m. Mountain Time, so we'll go ahead and get started. Welcome to the second installment of the NSC Virtual Lecture Series. This event is co-sponsored by the Nuclear Science and Security Consortium, a multi-institution initiative focused on training the next generation of nuclear security professionals while engaging in research and development with the national labs in support of the nation's nonproliferation mission. The NSSC works with 7 partner universities and 5 national laboratories, including LANL and Sandia, and is based out of the University of California, Berkeley. The talk today is part of the NSSC Virtual Learning Series, planned to support continued connection between students and national laboratory subject matter experts, particularly during the global pandemic. If you're interested in joining the NSSC community, you can get in touch through the email address listed on the slide, the nsscinfo@berkeley.edu. Opportunities with the NSSC include a bi-weekly mailing of job postings and events, additional online lectures, and conferences and summer programs focused on nuclear security science, technology, and policy. Our speaker, Dr. Alexis Trahan, will present her talk, and then we'll have some time for questions afterward. Please use the Q&A feature to ask your questions, and I'll be keeping an eye out for them. So we are joined this afternoon by Dr. Alexis Trahan, an R&D engineer with the Safeguards Science and Technology Group and the Senior Project Lead for NA241 International Nuclear Safeguards at LANL. She received her BS in Nuclear Engineering from UC Berkeley in 2011 and her MS and Ph.D. from the University of Michigan in 2012 and 2016, respectively. Alexis works on development of detection instrumentation and analytical methods with an emphasis on neutron detection for nonproliferation. She is currently developing and testing technologies for used power reactor and research reactor fuel characterization. Alexis is also actively engaged with the Nuclear Compliance Verification Program as the LANL Project Lead. So welcome, Alexis. You can go ahead and share your slides.
All right, thanks, Chloe. Let's see here. Start sharing my screen. All right, how's that look?
Looks all right to me.
Okay, awesome. All right, so thanks everyone for having me virtually here today. I'm excited to chat about non-destructive assay for nuclear safeguards. And so first of all, as you can probably tell, I'm sitting outside. I live in Los Alamos, New Mexico. We are dead in the middle here of monsoon season. So if you hear some thunder or see some lightning, don't be alarmed. That is totally normal. So today, as I said, we're going to talk about non-destructive assay. So I'm going to start talking a bit about safeguards in general, defining what are nuclear safeguards, and as well as talking a bit about the International Atomic Energy Agency. So international nuclear safeguards play a central role in preventing the spread of nuclear weapons in nuclear nonproliferation. And they're defined as a set of technical measures that are applied by the International Atomic Energy Agency, or IAEA, to independently verify that nuclear materials are not being diverted to illicit purposes, such as a weapons program. And so safeguards are implemented throughout the nuclear fuel cycle. They consist of tools and methods to account for and measure nuclear material, or to track nuclear material or contain it at various facilities throughout the fuel cycle. So some of the methods that are employed for safeguards include a nuclear material accountancy, or basically measuring nuclear material either destructively or non-destructively to see how much material is present and to account for it. And then there's containment and surveillance, which you heard about from Dr. Smart yesterday. So you've gotten a good intro here to safeguards in general. And then there's environmental sampling and unattended and remote monitoring. And all of these pieces play a crucial role in safeguards implementation by the IAEA. And today we're going to focus from a technical perspective on this component, the non-destructive assay piece. So I like to present this infographic on the IAEA. I get it from their website because it's just a nice, succinct way to get a visual of all it is that the IAEA does, because it really is a tremendous amount of work that the IAEA has to accomplish to, to support this mission of nonproliferation and prevention of, the spread of nuclear weapons. So the IAEA currently has comprehensive safeguards agreements in place with 100, this as of 2018. So actually these numbers are a little old. So when I say currently, I should say as of 2018. So as of that time, there are 183 states with comprehensive safeguards agreements in force. And that's just an agreement between a state and the IAEA, that the IAEA will come and implement safeguards in that state. And then there are 134 states, again, I think that number is a bit higher now in 2020, that have additional protocols in force. And so this is, a bit of additional safeguards on top of the comprehensive safeguards agreement that the IAEA will implement in that state once that agreement is in place. So, the IAEA is responsible for tracking over 200,000 significant quantities of nuclear material all around the world, and they do that in over 1,300 nuclear facilities. So it's really a huge amount of work. And the reason I like to show this infographic and talk about it before we get to non-destructive assay is because it's important to have this in the back of your mind as to just how much the scale and magnitude of work that's done by this agency. Because as we as engineers, when we're designing tools like for non-destructive assay, we need to think about efficiency and effectiveness and how the mission space as a whole, as opposed to just the technology. So keep that in mind as we move forward. So a few initiatives that, today, as of 2020, the IAEA is working to advance include universal acceptance of the additional protocol. So you saw there were more states on the previous slide with comprehensive safeguards agreements in place than with the additional protocol in place. And so the IAEA is working to have everyone sign on to the additional protocol. Safeguards by design are another really crucial initiative that the IAEA and member states support programs are working toward. And what that's about is, instead of building a facility and designing it and then coming in after the fact and saying, okay, how do we implement safeguards at this facility? It's just moving that process to the front end of the design. So instead, as you're getting ready to put together a design of a facility, you think about how safeguards can be incorporated, how material balance areas can be established, and how you'll account for nuclear material in that facility. So it's really saving the IAEA a lot of headaches in the end when that forethought has gone into the process. And let's see, unattended monitoring and data integration. So this one should be fairly obvious based on the previous slide, right? The IAEA has a tremendous amount of work to do and limited resources. And so the more unattended monitoring they can do, the more inspections and verification that they can do without having to have an inspector physically present at a facility at all times, the better they can do at fulfilling their mission and their objectives. And then lastly, there's the state level concept. So this, under the state level concept, the IAEA assesses each state as a whole. So rather than thinking about, an individual declared facility and, individual materials within said facility, they really think about the fuel cycle as a whole within a state. They think about, developing a state level approach, meaning how do we combine the information that we get from the safeguards measures in place, as well as open source literature review and any other signals that they have. How do they combine all of that to really get a full, complete picture of a state? And that's just to implement better safeguards. And then lastly, safeguards measures are traditionally established based on material attractiveness, and that continues to be the case. But now they're also thinking about path attractiveness, or what acquisition paths may exist in a state to obtain a nuclear weapon, and how do we make sure that the most attractive paths or the shortest paths to obtaining a weapon are fully covered by our safeguards measures. So it's just sort of a different way of looking at the same problem, which is, again, ultimately preventing the spread of nuclear weapons. That's the ultimate goal. And that's what, all of us who support the IAEA and safeguards mission are here to make happen. Okay, so that's my whole intro to nonproliferation, safeguards, IAEA. So now we're just going to get into the technical part, and that is the non-destructive assay. So NDA is the most commonly employed technique for material accountancy, and it's essentially typically a series of gamma or neutron detectors that are used to measure the radiation emitted from a sample of interest. So instead of just picking up, a piece of metal in a facility and saying, this is probably uranium, let's weigh it and say how much uranium exists in this facility, all metals pretty much look more or less the same. And so by measuring the radiation emitted from that sample, we can say definitively, with some uncertainty bars, how much material exists in that facility. And so signals that may be used, signatures that may be used from a sample to measure and quantify the sample include the energy of the radiation, the timing of detection of the radiation, and the intensity. And so depending on what kind of detectors you're using and what signature, what type of radiation you're detecting, you will be using some combination perhaps of these signatures. So you can break NDA up into two somewhat distinct categories, and that is passive and active NDA. So in passive NDA, we have some sample that's emitting radiation all by itself. We have some detector next to that sample, and we are measuring the radiation that's emitted. There's no external source. And then in active non-destructive assay, you have, again, your sample, and this time you have some irradiating source, perhaps a neutron or gamma source, and you're inducing some additional signal within your sample, and then measuring that subsequently induced signal with your detectors. So these two types of NDA are crucial for measuring different types of special nuclear material. So when we have a sample such as plutonium, there tends to be plutonium-240 present in the isotopic composition of your sample. And if you have plutonium-240, then you have spontaneous fission. And if you have spontaneous fission, then you have a strong passive radiation source. On the other hand, if we're looking at uranium, uranium may have, uranium-238 and uranium-235 primarily, and uranium-235 is a fissile isotope, so you're not really getting a passive emission from that, not much passive emission from that isotope. Uranium-238 is spontaneously fissioning, but at a very, very low rate. And so if you were to take a uranium sample and put it into a passive non-destructive assay system, you would measure for neutrons, you'd measure very, very little coming off. And so, you need, depending on the type of sample, the type of special nuclear material that you're looking at, and the type of radiation, those examples were for neutrons, then you're going to need a different type of non-destructive assay. Okay, so I like to talk a bit about neutrons and photons distinctly and as they apply to non-destructive assay. Because when you are detecting neutrons or detecting photons, the origins of the radiation, the signal that you typically measure, the shielding, and even the detectors that you use are going to be very different. So a lot of nuclear engineering students or people who are familiar with radiation detection at a university may spend a lot of time looking at photon detection or gamma ray detection in most cases. And so that's why I like this slide, because I think it's important to differentiate between the two. Because for the most of this talk, we're going to talk about neutrons, because I'm definitely a neutron person, so I'm a bit biased. But okay, so let's go over some of the differences. So for origins from neutrons are typically originating from spontaneous and induced fission within a special nuclear material sample, such as uranium or plutonium, or alpha N events. And that's where you have an alpha particle emitted. It interacts with a low Z element, and then it produces a single neutron. So those are your two primary neutron sources within special nuclear material samples. You may also have neutrons emitted from cosmic ray interactions, from PN, proton N, from N2N, gamma N, but those are far less common. So the vast, vast majority of the neutrons we detect are from spontaneous and induced fission and alpha N. For photons, on the other hand, when you get a gamma ray, those are what come from a nucleus, from nuclear interactions or nuclear collisions. And then when you're measuring X-rays, they come from the electron cloud. And so the important distinction there is based on what you're trying to quantify. If you're trying to determine an element, you can get that information from an X-ray. If you're looking for an isotope, you need to get that from gamma rays. Okay, so signal, and this is the really important one. When we measure gamma rays, we typically measure energy and intensity. So just how many gamma rays did we detect at some specific energy or in some specific energy bin, and that intensity or that number of gamma rays in that energy is what tells us how much material or how much of some isotope that's emitting that gamma ray is in our sample. Of course, there's some math there to go back and figure that out, but that is fundamentally how that works. Now, that same principle does not necessarily apply to neutrons. When we're measuring neutrons in non-destructive assay to quantify some isotope, the mass of an isotope or the mass of a material that we're looking at, we typically look at time of detection and correlations. And the reason for that is that essentially all neutrons emitted from fission are emitted in a Watt spectrum. And so with the energy spectrum being the same, we can't necessarily get a lot of information about what we're trying to, distinguishing between isotopes or materials with that method. Whereas when we look at time and correlations, what we're looking at essentially is for neutrons from fission. So as I mentioned before, spontaneous and induced fission are the two primary sources of neutron emissions in addition to the alpha N. But spontaneous and induced fission emit multiple neutrons at the same time, whereas alpha N reactions emit only a single neutron. And so we use that difference to differentiate between fission in a sample and alpha N or other reactions in a sample. And so we're going to get more into this concept in a few slides from now, but just suffice it to say for the time being that with neutrons, we're typically looking at time and correlations. With gamma rays, we're typically looking at energy. Okay, these two particle types are also shielded very differently, and that may really matter depending on what your sample is encased with. So we use a low Z material to shield neutrons, and we use high Z material to shield photons. And then lastly, the detectors that you'll choose from or use in a system are going to be different depending on whether you're trying to measure neutrons or photons. When you're measuring neutrons, sort of the most common NDA system detector is helium-3. There are also other detectors used, such as fission chambers, scintillators, but helium-3 you'll find quite a bit of the time in NDA systems. For gamma rays, we use high purity germanium often if you want to have good energy resolution, or you might use sodium iodide for slightly lower energy resolution, but a smaller, lighter instrument. And then there are scintillators again. So scintillators are a dual particle detector. You measure both neutrons and gamma rays, which of course is a benefit if you're trying to measure both particle types. It can be a drawback though, because if you have to be able to confidently distinguish between the two. So that's a whole different topic, but there's a few different detectors that you would use to measure each. Okay, so we're going to jump into neutrons now in neutron systems. And again, I do most of my research in neutron detection for non-destructive assay. So I'm going to spend a bit of time here. If you've ever heard me give a lecture before, you know I cannot get through 45 minutes without talking about neutron coincidence counting. So I'm going to give a little intro to that here as well. Okay, so a history of neutron counting for NDA. Back in the day, before electronics were really fast, before we had good processors in our data acquisition systems, we did total neutron counting. And that is just recording the total number of neutrons that were detected in a certain amount of time from some sample of nuclear material. And with this method, you can only obtain accurate assays for a few types of special nuclear material. Now, there are certainly applications and nuclear material types where total neutron counting is perfectly sufficient and will accomplish the goal that we're trying to accomplish with that system. However, it was discovered a few years down the road as electronics and processors got faster that if we instead did coincidence counting, we could obtain quite a bit more information about the sample being measured. So in coincidence counting, instead of just measuring the total number of neutrons within some period of time, we're recording how many times did we detect 2 neutrons within some set time window, or what we call a gate. And then that essentially is going to be proportional to the amount of fission taking place in our system. Again, there's a lot of math from A to B there, but that is the fundamental concept. And there's a wide application of coincidence counting within international safeguards. It's very useful for quantifying plutonium, for example, any spontaneous fissioning source, or any induced fission with an active interrogation. So, so coincidence counting is currently, I think, the most widely used neutron NDA method within standard neutron NDA systems. However, again, electronics got faster, processors got better, and we went on to neutron multiplicity counting. So this is just a logical extension from coincidence counting. Instead of looking for how many times did we detect 2 neutrons within some time gate, we say how many times did we detect 3 neutrons within some time gate, or 4 neutrons, or 5 neutrons. And that you could see how that could go on. So this obviously is even more information about our sample. This is, enables us to get another measurable parameter, or maybe multiple other measurable parameters that allow us to solve for more unknowns, in our equation of figuring out what mass of the item we're looking at. So the drawback here is that in order to have a multiplicity counting system, you need extraordinarily high efficiency. So with total neutron counting, the number of neutrons detected will be proportional to the efficiency of your detector system. If you've done any radiation detection, that makes sense, right? Number of neutrons detected proportional to efficiency. With coincidence counting, now we're looking for 2 neutrons detected, right? So the number of coincident events that we measure is proportional to the efficiency squared. Again, the logical extension, as we're looking for triples, or what we call triples is when we get 3 neutrons within a time gate, then the number of triples detected will be proportional to the efficiency cubed. And so this problem very quickly gets intractable. If you have, if you're looking for triplets or triples, you need to have an extremely efficient detector. And so there are a few multiplicity or counting systems, in the world. It is a very useful technique, but there are certainly limitations from a practical standpoint and a cost standpoint. It costs a lot of money to make such an efficient detector, that limit the application of multiplicity counting. So this is just kind of a simple image of what a coincidence counter design sort of looks like. It tends to be a sample counting well, where you have some fissioning source inside, and there are neutron detectors that surround that well and that material. And the reason for that, the reason you're surrounding, your material with detectors is, again, because efficiency is really crucial in neutron counting and coincidence counting in particular. Again, here we have helium-3 neutron detectors because they're a very common choice for neutron systems, neutron-based NDA systems. And so we're measuring the emission of multiple prompt neutrons from a fission event. And that is what we detect as coincident neutron events. So I like to do a little thought experiment to kind of understand, how coincidence counting works. So imagine that you have in your sample, which is sitting in your well surrounded by helium-3 tubes, that you have a spontaneous fission event in your material. And that spontaneous fission event emits 3 neutrons. So one of the neutrons thermalizes in your moderator, your high density polyethylene, and is detected. So you get one tick in time. Okay, your second neutron takes a little bit longer to thermalize, but then it is also detected. So you have a second tick, a second detection event a little later in time. Your third neutron goes on and causes another fission event. This time we have an induced fission in blue, and this time you've got one neutron that escapes, and the second neutron causes another fission event. This time 2 neutrons escape, 1 neutron is detected. So now we have this other event, later in time from those first 2, and this goes on, okay, until your fission chain ends, until all the neutrons are either detected or escape. So all of these neutrons that you see here, all these detections, are all correlated detection events. So all of these neutrons, one of them could not have existed without the other. They're all part of the same fission chain. So neutrons that come from the same fission chain, they are detected from the same fission chain or the same fission event, are called correlated neutrons. And you'll hear lots of terms for these: coincident neutrons, correlated neutrons, true coincidences, but they're all correlated, okay? So what's the problem? Why can't we just detect these neutrons and say, these are all correlated, great, now we know how long this fission chain was and how much fissionable material we have in our sample. And it's because you never actually just detect this, right? You never have a single fission chain happening in a system at one time. What you really have is something like this times 1,000 or 100,000 or 1,000,000. You've got tons and tons of overlapping fission chains all happening at the same time. And you're detecting neutrons from all of these overlapping fission chains, all with the same detectors. So how do you differentiate? How do you tell what comes from one fission chain versus what comes from another fission chain? And essentially the answer is that we use statistics. We measure enough neutrons and we measure long enough that we can say with some certainty over time what neutrons came, what percentage of the neutrons came from the same fission event or same fission chain, and which ones were just accidentally correlated. And the way that I like to visualize this, that I find the clearest to understand how that works, is with a Rossi-Alpha distribution. So that's what this distribution is here. So if we go back here, and I'm going to annotate here real quickly. Okay. So if we take the time, so remember, these are detected neutrons in time here at the bottom. If we take the time from this first neutron to the second neutron, that difference there, and we add it to a histogram, and the time from the first neutron to the third, and the first to the fourth, all the way down the row, and then we go the second neutron to the third, the second to the fourth, the second to the fifth, all the way down the row, and you repeat this for all of the detected neutrons. Let me see here. To turn off annotating to move to the next screen. I've made this mistake before. Okay. Oh, and then the annotation still shows up. Let's see. I'm going to clear all drawings. There we go. Okay. The joys of Zoom. So, if you do that, okay, you measure the time from every neutron to every other neutron in your detected neutrons, in your system, from all the detected neutrons in your system, you get a distribution that looks like this when you have a fissioning sample or a fissioning source. And so the reason for that is that when you have neutrons emitted simultaneously from fission or emitted very close together in time because they're from the same fission chain, then they're more likely to be detected close together in time. So when they're emitted at the same time, they're more likely to be detected close together in time. And that's what gives you, I'm going to annotate again at my peril, that is what gives you this region here, okay? So you're more likely to, again, get neutrons detected at close together in time. If this axis is a time difference between detections, you're more likely to get them close together than far apart in time. So what we do is we set 2 time gates. We say that whatever your triggering neutron was, or your first neutron and your difference of neutrons there, whatever your first neutron was, and I'm going to clear. and go back. Okay. If we're going from, you know, this first neutron on this mark, and then we, this one here, and then we get another neutron way down in time, you know, 1,000 microseconds later, we say physically, there's just no way with this detector system that this neutron here, what we call our trigger neutron, from this fission chain, could have come from the same fission chain as this one we detected, you know, way down here. Imagine this time axis is extended way down here in time. There's just no way that that neutron down there could have come from the same fission chain as this one. It's too far out in time. And by doing that, by setting that time window, you know, way out there in time, that allows us to quantify how many accidental neutron coincidences we have. So again, we set this gate way down here. We see how many neutrons are accidentally correlated, and then we can subtract that from this region here, and it gives you the simplest equation in all of science, R plus A minus A, and that gives you your real coincidences, or R. Okay? So that's how we get that is neutron coincidence counting in a nutshell. It's a somewhat complex topic. It's both complex and simple. I don't know how that's possible, but essentially we can use that real coincident rate to determine the fissile content or the the fissioning content in whatever sample we're measuring. Okay, clear all drawings and let's move on. So this is an example of a neutron multiplicity counter, or this one here is the epithermal neutron multiplicity counter, or ENMC. The efficiency of this system is 65%. So it's very high efficiency in order to be able to do triples counting, to do multiplicity counting. The die-away time of this system is 22 microseconds, which just means that's how long on average neutrons live in the system. It has 121 helium-3 tubes, so it is definitely not a cheap system, and that's the reason that you don't just find these in every lab all over the world. But it allows you to do some very interesting analysis of nuclear material that is really not possible with coincidence counting. And if I had more time, I'd go into what all that means. But anyway, suffice it to say, here's an image of a multiplicity counter, and you can particularly do impure items, which is very useful. Okay, so we're going to move on to gamma rays. Check my time. I think we're doing okay here. So gamma rays are also an extremely important part of nondestructive assay, and are even used more often, in nondestructive assay than neutrons. And so I'm going to give a couple examples of how we might use gamma ray detection to quantify specific special nuclear materials we might be interested in. So we know that different isotopes of special nuclear materials, such as plutonium-239 versus plutonium-240 versus plutonium-241, different isotopes will emit gamma rays at unique energies and in predictable ratios. And so by measuring the peaks, the energies of gamma rays that come from these different isotopes, and measuring the intensity, so how often do we get some gamma ray of some energy, which we know is associated with a specific isotope, then that will enable us to quantify the amount of that isotope in the material you're measuring. So there are software programs that are designed to basically do the hard part of this for you. What you measure might look like the white dotted curve here in the spectrum at the top. And what actually creates that spectrum is the addition of all of these individual peaks. And so MGA, or multi-group analysis software, can take into account the detector's energy efficiency curves, assumptions about self-shielding and sample attenuation, and then reconstruct the individual contributions. And it will tell you then what are the relative abundances of the different isotopes that are present in your sample. So note that I didn't say when we were talking about neutrons that we could get specific necessarily isotopic contributions. You can get the mass of a sample, and we can kind of generally figure out what are the contributions if we make assumptions about the relative isotopic concentrations. But really, if you really want to be certain, ideally you would do a gamma spectroscopy measurement on some sample to get the isotopic composition, combined with a neutron measurement to get the mass, and then you can get the masses of each isotope in your sample with a much higher degree of certainty. And then I threw this in there just for fun because, so I'm a spent fuel person in addition to being a neutron person. And I think this is a really interesting gamma ray based non-destructive assay system for spent fuel measurement in particular. So spent fuel is a whole different, brand of nuclear material. It's much more complicated. It's not just uranium or just plutonium. It's a mix of uranium, plutonium, higher actinides, fission products. It's a big mess. And so developing an NDA system to measure it is really challenging. And this system, PJET, or passive gamma emission tomography, has been in the works for a few decades now and is ready to be deployed. And this system has 2 boron-10 detectors for neutrons and 174 collimated CZT detectors for gammas. And so it can also do gamma spectroscopy. It can get the cesium ratio, which you use for burnup determination in spent fuel. If these words mean nothing to you, I'm sorry, just ignore this slide. But essentially it combines gamma spectroscopy, tomography, and neutron detection to give you a really complete picture of the spent fuel that you're looking at. So it's a really interesting system, and it's going to be placed at least at one geological repository for measurement of fuel before it goes down into the Earth. Okay, so we are going to move on to heat now, the last of our signatures for non-destructive assay. And I haven't even brought up heat yet to this point, because really heat is still a measurement of gamma rays and neutrons, right? That's what's giving the heat, are these particles. But it's a different way of measuring. So calorimetry is a very well-established and precise method of non-destructive assay. It's been around a long time, and it gives very accurate answers. It tends to be more accurate than, say, the neutron and gamma systems that I've presented so far. And it uses that thermal power that's generated by the radioactive decay to determine the mass of special nuclear material. So if this is a more accurate NDA method, why not just use it all the time instead of the other systems I've presented? And the reason for that is that you have to fully encase, with this type of calorimetry system, fully encase a sample within a calorimetry system. So that limits the size of what you're measuring. And also it takes quite a bit longer than standard non-destructive assay techniques. And so there are instances where calorimetry is both desirable and even preferable. But then there are also instances where it's not plausible. It's, for whatever reason with the inspection environment or, agreements in place, for whatever reason, it just takes too long and it is not practical. So, anyways, calorimetry, it's in use at LANL for our material accountancy. It's in use all over the place, but it is a little more limited perhaps in its applications. And then this, so I give a lot of these NDA talks. I really enjoy talking about non-destructive assay. And this talk is the first time that I've included some slides on microcalorimetry. And this is kind of an up-and-coming NDA technique or methodology where they're using ultra-high energy resolution microcalorimeters to basically overcome all of the performance limitations that exist in the NDA instruments I've talked about. They have 10 to 50 times better energy resolution than semiconductors, for example. And so that is a huge improvement. And what to me really stands out in thinking about high purity germanium is this plot down at the bottom right here, where you can see the resolution that you get in peaks from microcalorimetry versus high purity germanium, which is kind of considered to be the gold standard in resolution, or used to be in the past. Clearly that gold standard is changing. So you can imagine a case where if you can do this kind of, where you can obtain this kind of resolution, that you could obtain a lot more accurate answer and a lot more accurate picture of what's in your sample. So microcalorimeters measure the heat energy of the individual photons or nuclear decays. And this is just a nice little picture on the left here. But again, it's really just a gamma spectroscopy kind of system, but it's a totally different way of measuring, what's coming out of your sample. It's measuring the heat instead of just the gamma ray energy. So this, again, here's a plot that really makes you think that perhaps microcalorimetry will become kind of a new standard in resolution for gamma ray detection, where you can see here high purity germanium detection of a uranium sample versus the microcalorimetry detection. And so, microcalorimetry has some challenges. It's pretty infrastructure heavy, and versus like a high purity germanium, for example. But as the research continues in this area, and as these detectors get smaller and easier to use and more widespread, then we may see an advancement in our capabilities for spectroscopy for non-destructive assay. Okay, so my last slide here, which I think we're looking pretty good on time. We'll have some time for questions at the end. So my last slide here is just kind of I wanted to give a quick overview of what we at Los Alamos do to support the International Atomic Energy Agency and the Safeguards mission in general. So we have been supporting the IAEA through Safeguards development for over 50 years now. And we do that through technology development. Essentially, every neutron-based NDA system employed by the IAEA came out of Los Alamos. So we really have, particularly a long history of neutron system development, as well as gamma system. And then again, now we're working toward this microcalorimetry. So we, technology development and NDA development continues to be our bread and butter here at Los Alamos and the Safeguards group. In addition to training, we do a great deal of training. So every IAEA inspector since the 1980s has come to Los Alamos for training in non-destructive assay system use. And we don't only train them how to, operate a system, because anyone can learn how to press a button and read a result. But, what we train is how to really think critically about the result that they're obtaining and how to understand the non-destructive assay instruments and why we use them, and how to obtain the best answer to really support them in doing, the best inspection job that they can do. And again, this is all just to support the IAEA in this really crucial mission of nonproliferation, of preventing the spread of nuclear weapons. And then lastly, expertise. So, we develop analysis algorithms, we send experts over to the IAEA to work with them directly through the, the International Nuclear Safeguards Office. And so, we take a lot of pride in our support of the IAEA and our support of the Safeguards mission. And I would be really happy to answer any questions that you guys have. So thank you for listening. And yeah, I would like to turn it over to question and answer.
Thanks, Alexis. So anyone who has a question can put it in the Q&A at this time.
The cons of microcalorimetry, great question. And so, I mean, microcalorimetry is still very much in the research and development phase. There's a lot of, you can't really understate how crucial it is to have a system that's been validated and verified and tested in a wide variety of situations. And I firmly believe microcalorimetry will get to that point, but right now it's still very much an R&D. So that's one drawback. It also takes, as I said, more infrastructure. It's a bigger system requiring, more parts to move around than, say your standard handheld gamma spectroscopy system. So, so there are certainly cases where it will be more useful and cases where it may not be usable at all. But as the R&D continues and as the system gets smaller and lighter and perhaps easier to use, some of those drawbacks will go away. The footprint of PJET. Ooh, such a good question. I've seen it in person, so I'm trying to picture exactly how big it is. I want to say it's maybe 3 feet across. So it's a donut shape, right? And it gets installed down in a spent fuel pool, and then fuel is brought over to PJET, inserted into the hole in the center. PJET does its thing, and it has rotating detectors inside of that annulus, inside of the donut shape, to produce this tomographic image. It's really fascinating. I really recommend, if you're interested in it, to you know, pull up an article on it, or if you email me, I can send you one. But yeah, it's a really interesting piece of equipment, piece of technology. I think, you know, if you're interested in NDA, it doesn't get a lot more interesting than PJET. It's such a complicated and, you know, fascinating system. So yeah, I want to say about 3 feet across, but I hope I'm not totally wrong on that. I'll have to look. Let's see. Let's see, I'm looking at the top here. What would you say is the biggest or most fundamental challenge scientifically in NDA neutronics, photonics, and calorimetry? So a great question again. And I mean, this will just be, I guess, you ask a different person, you may get a different answer, but I would say it's uncertainty. So, you know, uncertainty tends to really be the limiting factor in NDA's applicability. Depending on what your uncertainty requirements are, it may not be useful at all. And that's why destructive analysis, which obviously I didn't talk about at all today because this was an NDA talk, but destructive analysis is a really crucial, you know, sister analysis method to NDA. And it's where, you know, you're going to shave off some of the material and measure it in some mass spectrometer or some other system where you get a really, really precise answer, and you have very, very low uncertainty. And you're just not going to get that with NDA. The uncertainty tends to be the limiting factor. So that's what I would say, is that we're always working on reducing that uncertainty. That continues to be a challenge. There are other challenges. Helium-3 is really hard to obtain these days, and so there's, you know, effort that goes into finding neutron systems that aren't based on helium-3, and so there are others, but I would say uncertainty if I had to pick one. Let's see. Can you speak about where spintronic spin-based neutron detection fits into the bigger picture of NDA? It's a great question, and I don't think that I haven't seen a system specifically, you know, based around spintronic or spin-based neutron detection. So I don't know how to answer that, in the sense that I haven't seen that system. So how it fits into the bigger picture, I'm not exactly sure. My hunch is that level of sensitivity would be difficult for NDA as a whole. So I mean, NDA is really about measuring a whole big sample. If you're measuring to that kind of sensitivity, you typically are going to need, I would imagine, a smaller sample size, maybe even a destructive analysis type sample size. So it's a good question in an area I'm not all that familiar with, but that would be my guess. Let's see, are labs in the US or in Europe or elsewhere taking the same or different approaches to NDA R&D? Another great question, thank you, Yana. So I think that in general, we all tend to be in pretty good agreement about what the needs are in NDA. I mean, you know, reducing the uncertainty, being less susceptible to background and cosmic rays. You know, a lot of these themes, they're true no matter where you are. So I think that is fairly consistent. You know, there are also there are standard commercial off-the-shelf, you know, they've been commercialized NDA systems that are used all around the world. A lot of them came, you know, from Los Alamos, as I said, especially Neutron systems. But once they've been, you know, commercialized, then they can be used in nuclear facilities all around the world. So, you know, I think that we in the US do a lot of R&D and NDA, but I don't think we're unique in that. I think that a lot of European countries also do R&D and NDA. And I think maybe just the emphasis is a little different. Like, for example, in Finland and Sweden, where they've got repositories coming online, they're pretty actively looking at NDA for spent fuel. Whereas, you know, in other areas of the world where they're trying to assess trying to solve different problems within safeguards, they might be putting R&D effort into different NDA systems with different applications. Okay, any thoughts on applying machine learning methods for NDA and the issue of quantifying uncertainty in machine learning approaches? Another awesome question. Yes. So we absolutely are looking at machine learning for non-destructive assay, as is the IAEA. This is definitely on the forefront of everyone's mind. So, you know, we obtain a great deal of data with non-destructive assay systems, as well as, you know, with other safeguard systems, with, you know, surveillance systems and others. And so applying machine learning is just the sort of logical next step. Like, of course, we would want to use some better way of looking at the data and processing it and understanding, finding the trends and patterns in the data with machine learning, as opposed to a human trying to figure that out. So, so the answer is that a lot of people are looking into that, even here at Los Alamos, or I should say maybe especially here at Los Alamos. There are people in the Safeguards group who are actively researching application of machine learning methods to non-destructive assay. Quantifying uncertainty in machine learning approaches is something I'm not that familiar with. I could definitely connect you with someone who is in our group if you're interested in following up on that. But I would definitely say, you know, application of machine learning to this problem is a hot topic, both at the IAEA and at LANL. And I think it's the future of Safeguards data analysis for sure.
I guess I have a two-part question for you, Alexis.
Okay.
So do you have any current projects that you're excited about that you can speak about? And then what kind of opportunities exist for students who are interested in that kind of work?
Great. Yes. Thank you, Chloe. So yeah, as I mentioned, I work in spent fuel, non-destructive assay. And so I work with a system called the Advanced Experimental Fuel Counter. This is a neutron coincidence counting based system for research reactor fuel characterization. And so we're constantly working on, you know, combining simulated and experimental data to construct calibration curves to relate a measured, you know, coincident neutron rate with a known, you know, fissile or an unknown fissile mass in an assembly. So we want to construct a calibration curve with known assemblies, and then theoretically apply that to unknown assemblies to determine their fissile mass. So a lot of interesting, you know, projects with the AEFC right now. We have an ongoing collaboration with Israel, with Thoric Nuclear Research Center, to measure their spent fuel from their Israel Research Reactor 1. And we just published a paper on that this year. So yeah, lots of interesting work in the spent fuel domain. And as far as, you know, students who might be interested, we love student interns. We love to have postdocs. You know, if you're graduating soon, please let me know and you're interested in this area, or if you're looking for a summer internship, I would love to, you know, we always like to bring in more students. We think, I mean, perhaps I'm biased, but we do a lot of really interesting science and really interesting work for a crucial mission in our group. So, you know, if this is something that interests you, please do feel free to follow up with me or Chloe. And we can absolutely, you know, help you to find where you might be able to pursue an internship or postdoc with our group. Let's see. Estimates of plutonium and other special nuclear material content of spent fuel is currently based on calculations of burnup. That's correct. How might IAEA handle discrepancies between calculated special nuclear material content declared by a state and an NDA measurement by PJET or other high precision NDA method for measuring special nuclear material and spent fuel? Okay, great question. And I'm going to try not to spend the next 10 minutes answering it, because there's a lot to this question. So, okay, so first of all, PJET, while it will do a confirmation of burnup using a cesium ratio, I wouldn't necessarily call it a high precision NDA method. What it really does phenomenally well, and which is really of importance to the IAEA, is it produces that tomographic image. So if there were a single pin, taken from an assembly, PJET and the image it produces should show that. Okay, so that's really important. And that is something that verifying the completeness of assemblies is a very high priority for the IAEA. So, you know, that has nothing to do with models, right? That's just verifying completeness of an assembly. Now, as you said, burn-up codes are used to determine estimates of plutonium in spent fuel, and that remains to be true. That is still the case. So, you know, if you did a measurement such as PJET, if you use a system such as PJET, and you measured the cesium ratio, and the burn-up that you determined using that cesium ratio was considerably different than what was declared, than, you know, what they said was the burn-up of the assembly, then definitely follow-on, you know, work would have to be done. But I wouldn't say, I mean, so certainly PJET is not determining a plutonium composition of the fuel. It's determining burn-up using the cesium ratio, but that is there, you know, it is different from like a plutonium mass, certainly by a lot. As more precise, or, you know, as more precise spent fuel NDA systems come online, that certainly may present issues, but there's a lot more to this problem. Again, I could talk about this one all day, but there are actually a lot of problems with the burn-up codes themselves, right? We know that, especially with power reactor fuel, that there exists a lot of deficiencies in the nuclear data, in the cross-section data, in determining that plutonium content. So even that number really is not, you know, what we get from the models of spent fuel, especially power reactor fuel, is not necessarily ground truth. And, you know, a lot of work is going in, I know, in the modeling community into improving the nuclear data that most affects the spent fuel models. And that's something I personally am interested in as well, being, you know, a spent fuel person. But yeah, so at this point, there really is no NDA system that's going to overturn anything a model says. Nothing is quite that precise. And this is all power reactor, by the way. So research reactor, different issue. But I assume you're talking about power reactor here, because that's where you get more plutonium. So hopefully that answers your question. If you want to email me, I'd be happy to talk more about this, because it's an interesting, very interesting problem. Thank you all very much for the very thoughtful questions. I really appreciate it. And thank you all for tuning in too.
Great, thanks, Alexis. And if you maybe want to put your email address in the chat for anyone who's interested in contacting you.
Let me see if I can figure out how to do that. I don't think it's letting me enter a question, but it's A Trahan, A-T-R-A-H-A-N @lanl.gov. I guess I could annotate it on the slide.
I think we can't do Q&A, but you could type it in the chat, but that works just as well. Perfect.
There you go.
All right. Thank you, everyone, and thank you, Alexis, for joining us this afternoon. I think this lecture concludes the NSSC virtual lecture series, but you know, if you have any questions about the NSSC or about Los Alamos, please reach out. We'd love to hear from you.
Thanks, everyone.